Okay, everybody, I want to remind you some stuff that we talked about with the line integrals. In particular, the work done by a force field on an object as it moves along a curve. Right? We showed in class that that work can be rewritten as a line integral, right? This is a certain form of a line integral of a vector field, we call it. And then we showed with a little bit of manipulation that we could rewrite this integral two different ways. Like this, we refer to this version of it, the tangential component of the force, right? So the work done by a force is entirely done by its tangential component. So that's the usefulness, I guess, of this version right here. But we also saw that we could rewrite it in terms of this as well. Okay, this right here is often referred to as the differential form. Well, for the obvious reasons, it's got the differentials dx and dy. Now, this is for a function, vector valued function with two components, but of course we could extend the logic to 3 dimensions, just add one more component, okay? And just to kind of give you a little bit of a visual, right? Here's a curve C, here's the unit tangent vector, for example, and maybe just one of the many arrows that the vector field would generate, okay? We imagine that this force field is maybe pushing an object along the curve. And that curve is given parametrically as usual, right? The way that we learned about vector value functions of one independent variable, okay? Now, we also said that if the curve is a closed curve, right? If the curve, excuse me, is a closed curve, then we would add these little ornaments to the integral symbol, these little circles, right? And that was just a way to emphasize that the curve was closed, okay? Now, we also said, right, if that's the case, then we refined the interpretation of this particular version of the line integral, and we called that the circulation of the vector field. And the easy way to visualize that is to imagine that the vector field is a velocity field for a moving fluid, right? And we said that this would give a numerical measure of the tendency of the fluid to turn the curve as the vector field swirls around it. Okay, so something like that might look like this. Let's say we got a curve, something like this, closed curve, oriented this way. Okay, maybe the velocity field, you've got a bunch of arrows looking something like this. All right, so that's your vector field, okay? And notice that as the vector field swirls around the curve, you can visualize the tendency for the fluid to swirl and cause motion in the curve, okay? So we refer to that numerical measure as circulation, okay? Now, we did say in class, what about this? Okay, so we have something for the circulation, the tangential component of the force, right? We've got something for that. And we remember that t is the unit tangent vector, but we also remember from our earlier work that there was a principal unit normal vector, and that was capital N. So like, how does that figure in? Well, let's see what we can do with this, okay? All right. First, as a reminder, the unit tangent vector, by definition, is this. Okay, now I'm going to rewrite that this way. Okay, and be mindful again, the denominator, that's speed. So I can write this way. Right, the camera's a little out of focus. It'll come back. Let's see if it'll come back if I do something like this. There we go. All right, fingers crossed. All right, so what I'm going to do next is distribute this through. Okay, and if you notice, again, that's actually that's version 1 of the chain rule, 2 instances of it. So the unit tangent vector can actually be written in this form. Now, the usefulness of that, no fraction, no denominator. Okay, it's still a unit vector. Its magnitude is still equal to 1. That's not going to change. It's just a different version of it with no denominator. It's a convenience. All right, that's it. It's just a convenience. All right, now let's consider We've got some curve. Here's its orientation. We'll call it capital C. All right. And then we want to add to that, maybe here, okay? There's my unit tangent vector. But notice, gang, the independent variable now is the arc length parameter, okay? The arc length parameter. So I'm writing T of S, okay? Now, from our earlier lectures, right, we know that the principal unit normal vector points towards the concave side of the curve. That would be this, okay? But for our purposes, what we're interested in is fluid flow that crosses through the curve and away from the curve. All right. So we've talked about circulation. That would be the flow of the vector field around or along the curve. Okay. That's our circulation. But what about fluid that goes across the curve? Okay. So that's what we're interested in. How can we determine the flow of the fluid across the curve? Well, for that, we need a normal vector that points away from the curve, still orthogonal to T, just not the principal unit normal vector. We want this one. Now, to distinguish it from this principal unit normal vector, let's not use capital N. Let's use this symbol instead. Lowercase n, we'll put that little hat on it to remind ourselves that it's a unit vector, okay? All right, now to get that to happen, what we need is a clockwise rotation through 90 degrees. Think of it that way, all right? To get from here to the unit tangent vector to where the unit normal vector is, right here, this one, we need a clockwise rotation of 90 degrees. Okay, that makes sense? All right, now think about this, right? Again, in our very early days of talking about vectors, right, we showed that any vector could be rewritten like this. The magnitude of the vector times the cosine of theta, magnitude of the vector times the sine of theta. Okay, you remember that? So in a similar way, I can write my unit tangent vector. Watch this, my unit tangent vector like this. Why don't I have the magnitude of the vector here and here? Because the magnitude of the unit vector t is just one. There's no sense in writing ones there. Okay. Now think about this. I want a new vector that comes from this old one by rotating the old one through a clockwise rotation of 90 degrees. Now remember, gang, from trigonometry, clockwise, that means not positive 90 degrees, that means negative. And so think like this. Okay, now that's me being lazy. We usually use radians, right? So it should be minus pi over 2. That's just me being lazy. Okay. But we should use the radians. Okay, that's typically how we do things. Now, gang, remember, so that's this right here. That's what I want to take my normal vector to be. So I'm going to write n with the little hat over it to be this new vector. Now, remember, again, from our trigonometry days and even our pre-calculus days, what does that mean? That's a horizontal shift to the right, pi over 2 radians. You know what's going to happen? That cosine is going to land right on top of sine, right? And then sine of theta minus 90, you're taking the sine function and you're shifting it 90 or pi, I'm sorry, pi over 2 radians to the right. What is that going to look like? That's what you're going to get. Okay, when you take the cosine function, gang, and you shift it pi over 2 radians to the right, it lands right on top of the sine function. So this becomes this. Do the same thing with the sine. And what it does is it falls on top of the opposite of the cosine function. That's how I got minus cosine of theta here. Okay, so we're just using a little bit of trigonometry and a little bit of work that we did in our pre-calculus days, horizontally shifting graphs. Okay, and so what I'll do is with this in mind, okay, we've got, here we go. Here's capital T right here. Let me write like this. Okay, here's capital T. And so why don't we notice then here, I wrote it again here in terms of cosine and sine, but look at N. What did it really come down to? Flipping both of these two things. We flipped them and took the opposite of the second one. Look what happens if you take the dot product of the two. What do you get if you take the dot product of the two? Yeah, exactly. You're going to get 0. Cosine times sine plus sine times negative cosine. Exactly. So their dot product is 0. So that means that the two vectors are orthogonal to each other. So it comes down to this. We took the tangent vector, flipped the components, and took the opposite of the second component. Okay. So in a similar way, using these components right here, I'm going to say we will write our unit normal vector n. Okay. Flip these two. Take the opposite of the second. Okay. Now, next thing I'm going to do is I'm going to take that vector and I'm going to dot it with f. The expression in particular, f dot n ds. What will I get from my trouble? Okay, notice that the ds here will cancel with these. Okay, and so we say the integral of f dotted with n ds is equal to the line integral of this expression. This we called the flux of the vector field f across the curve C. Okay, so we had something. Let me see if I can find, where's that on my, here we go, right here, right here. Okay, we had something for the tangential component of the force, right? We had an integral for that. And we asked ourselves, well, what about the normal component? What can we say about that? What does that mean? Okay, and through all of this work that we just did, okay, we've now come up with a representation for a line integral that contains the normal component of the force, and it's equal to this integral in differential form. Okay, so that's how you get from one to the other. And what is its interpretation? We call that the flux of the vector field across the curve C.